Alright, in this lecture we hope to explain the reaction time lab. Since it's a touch of reality for the kids, there's a lot of studies done that show a difference of 0.24 seconds in human reaction time. You may have seen that it was tougher to catch the meter stick whenever you were eating or drinking or texting on your cell phone, and hopefully you can relate that to driving. So, our learning goals for this presentation are that you should be able to determine situations in which final velocity is not easily measured. We can't always measure all the variables, and there are certain situations in which we can't measure final velocity. You should be able to determine the origin of the third motion equation. So this is our actual third motion equation that deals with acceleration and time and velocity. And you should be able to determine an unknown using this equation right here. Now this equation is listed just like this on the formula chart, and you should be able to use it. So, the reaction time investigation. Final velocity was not easily measured. We knew it started at rest because you dropped it, and whenever you dropped it, it wasn't moving to begin with. You know the acceleration there. The acceleration was that of gravity, which is a constant, and you could easily measure the distance by marking where you caught it on a meter stick. But in this case, measuring final velocity would be very, very difficult as far as how fast the ruler is moving when you catch it. So because of this is a situation in which you can't actually find the final velocity, so what do? So far, all of our equations have final velocity in them. But it turns out that if you take these two equations, so in the first one we expanded this equation out and we said, okay, it's 1/2 VF plus VI times t. And in the second equation we had this. It was our definition of acceleration from our graph. Well, you can actually rearrange this equation of this. And this is actually the more common version of this equation in textbooks. Now on the formula chart, this is actually the formula chart version. Okay, but this right here is what you'll see in the majority of textbooks if you take this class in college or if you're reading your textbook now. So this right here is the common version. Well, if you take this equation right here and you actually substitute in, you solve this thing for final velocity and you plug it in here, whenever you do that you can actually eliminate the final velocity term. And when you do that, this is what you get, which simplifies to our equation that we have here, this delta D equals VIT plus 1/2 AT squared. Now, there are no new variables here, so we don't really have to go through these other than to say, delta D is displacement, which is measured in meters. We know that VI is initial velocity, and that's measured in meters per second. We know that acceleration is meters per second squared, and we know that time is delta T, and it's measured in seconds. You should be able to fill in all these from memory, and if you can't, you need to look back through your notes to make sure that you know them moving forward. So in this example, it says determine the initial velocity of a car that accelerates at 2 meters per second. So we say, okay, this right here, look at it, it's meters per second for 10 seconds when moving in the positive x direction for 500 meters. Okay, in this example, we have a car that's initially traveling to the right for 10 seconds. It's accelerating at 5 meters per second squared. So we know that this is a distance or a displacement of 500 meters. Displacement. We know that acceleration is measured in meters per second squared. So we have meters per second squared. And we also know that time is 10 seconds. And we know that we are trying to solve for the initial velocity. So the principle that we're going to be using is we're going to be using accelerated motion, and then we can do the formula. The formula that we're going to use in this case is D equals VIT plus 1/2 AT squared. And if we look, I'm trying to solve for VI. I have D, I have A, and I have T. So there's no extra information, but I definitely have everything that I need. So now we can say there's no irrelevant information, and we can go ahead and solve this question. So we plug in for the displacement. We plug in 500 equals VI times 10 plus 1/2 of 5 times 10 squared. At this point, you can go ahead and do some math, and we can say, okay, 500 equals 10 VI plus 10 squared is 100, times 5 is 500, divided by 2 is 250. We subtract 250 from both sides, and when we do that we get 250 equals 10 VI. We divide both sides by 10, and when we do that we get VI is 25 meters per second. This example, it says determine the acceleration of a rocket that starts from rest and accelerates over 5 seconds for 100 meters. Now a lot of people see and accelerates for 5 and they just automatically think, oh okay, well acceleration is 5. That's not the case. It's always key to take a look at the units and realize that it's 5 seconds there, which indicates that it's a time. So it's really important that you look and see what's actually there. You should be able to figure out this question, plug in your answer or your information, and solve that the acceleration ends up being 8 meters per second squared. In this example, it says determine the total displacement of the car. You should be able to figure out independently that the displacement of the car is 75 meters, and you should be able to justify that based on the information in the problem. Now, so far, we have dealt with the questions that are exclusively in the horizontal. So everything's moved left or right, flat on even ground. Well, we know most often the case that is not true. Most of the time, objects move vertically. In fact, they move up or down more easily than they move left or right. So there's specific things as far as a vertical situation is concerned. If you look, there's a key factor between all of these, and that is the acceleration. The acceleration right here, in all of these situations, whether an object is thrown up, whether an object is thrown down, whether an object is at its highest point, it doesn't matter. Whenever an object is allowed to move vertically, it has an acceleration of negative 9.8 meters per second squared. That is because it is the acceleration of gravity. Gravity does not change based on whether you drop a ball, throw it down, throw it up, whether it's at its highest point. Earth's gravity is always the same number. For some reason, people always want to say, oh, well, when it reaches the top of its path, it actually stops and its acceleration is 0. That's not the case. The acceleration is always negative 9.8 meters per second squared. You cannot change gravity based on what you do with a ball. Now, we have a couple of key situations. This is an object is dropped. Anytime you see the term drop, that's an indication that you're going to have an initial velocity of 0. Okay, a lot of times they'll say an object is dropped and give you one piece of information, and it looks like there's not enough. But you've got to look for key terms like drop. Another is an object is thrown down. Whenever the object is thrown down, you're going to have to go ahead and say that the initial velocity is negative because it's moving down, just like the acceleration is negative as it's moving down. And at the highest point, whenever you take an object and you throw it up in the air, when it reaches its highest point, its velocity actually becomes 0 because the object goes up, 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 stops, and then comes back down. So for that brief instant where it's at its highest point, its velocity is 0. So these are just a couple of key situations. You can look for these whenever you're trying to solve problems. In this example, it says a ball is thrown up at 20 meters per second, so we know that's going to be positive. How long will it take for the ball to be 10 meters from its starting position? Okay, in this example, we start off with what we know. We know we have a ball that is being thrown upwards from the ground, and it is initially thrown at 20 meters per second. And from that 20 meters per second, we want to know at what time it's going to reach 10 meters. So that's what we want to know. So now we can say, okay, well, we know when we throw the ball up in the air, it's going to be under the influence of gravity. It's going to turn around and come back down. So that should kind of give you a clue that there's actually going to be 2 places where the ball is going to be at 10 meters. So we're looking for a solution with 2 possible answers. So let's look at what we know. So what do we know? In the given information we have the initial velocity is 20 meters per second. We know that the acceleration due to gravity is negative 9.8 meters per second squared. We also know that we want to know the displacement is 10 meters. We want to know at what time it's 10 meters away. So now let's take a look. If we go to our find, we are trying to solve for the time. So we know we're talking about accelerated motion at this point. So now we scroll back and we say, okay, the formula that I'm going to be using is going to be the formula delta D equals VIT plus 1/2 a t squared. There is no irrelevant information in this problem, and what we're trying to do is we're trying to solve for t. So now if we start and we say, okay, what do we know? Okay, we know that we have 10 equals 20t minus, which would be plus 1/2 negative 9.8 t squared. Now if you look, you know this is going to have two solutions because you have a quadratic formula here, and that's exactly what we were looking for. So now let's take a look. We're going to go ahead and rearrange this thing. First we're going to multiply this out, and when we do that we're going to get 10 equals 20t minus 4.9 t squared. So now we're going to move everything over to one side. We're going to say 4.9 t squared minus 20t equals, or excuse me, plus 10 equals 0. Okay, so this right here, what we did is we took these right here and we moved them to the other side. When we did that, we had to change the sign, so negative became plus, plus became negative. Well, now this is in the formula, this is in the format for a quadratic formula equation. Remember the quadratic formula is x equals negative b plus or minus the square root of b squared minus 4ac divided by 2a. Well, if you look right here, this is our a term, our b term, and our c term. So now we can say t, because we're looking for t, is equal to negative b, this is my b term, so it's going to be a positive 20, plus or minus the square root of b squared, negative 20 squared, minus 4ac divided by 2a. So now when you do the math here, you end up simplifying the expression to where you get 20 plus or minus 14.3 divided by 9.8. So now it gets a little tougher from here because you say, so now what do? We say, okay, what solution am I going to take, the plus or the minus? And remember, we were looking for two solutions. So the fact that we were looking for two solutions is actually pretty good here. So now we can take this thing and we'll say, first of all, we'll do 20 minus. So when we do 20 minus 14.3 and divide it by 9.8, we get a time of 0.58 seconds. And when we do 20 plus 14.3 and divide by 9.8, we get the time of 3.5 seconds. This question says, determine the displacement of a ball that is dropped 10 seconds after it was dropped. So just right away, you know it's dropped, so you know you're going to have an initial velocity of 0, and you know the displacement is actually going to end up being negative because the ball is going to actually end up below where it started. You should be able to figure out that the answer to this particular question is negative 490 meters. On this one it says, determine the time for a ball is in the air if it's dropped from a 100-meter cliff. Well, in this particular case it says, well, you should be able to figure out that the answer is 4.52 seconds, and you should be able to justify that answer using equations and solving for it to match what you have.